homework, right? So, how we doing, okay? Devin.
Just curious, what's the next thing we learn?
Right now?
Yes.
We're going to go back to 5.4 right now. We skipped one section of Chapter 5.
Where do we start in Chapter 7? That's what I was trying to...
Oh, Chapter 7? So Section 4 has some nice pictures that can help you understand. If I zoom in, we can actually see it. So let's do that. Even and odd functions. So I guess I should talk about this again. What's it mean to be an even function or an odd function?
F of negative x equals x.
Yes, you always check f of negative x. So let me write down the rules here, right? So even. F of x is even if f of negative x is the same as f of x, like Dan said. And then f of x is odd if f of negative x equals what? Negative f of x, okay? Both of these involve symmetry. We mentioned last time that another way to say even is symmetric with respect to which axis?
Why?
The y-axis. Whereas this one, we didn't mention this last time, but I'll tell you it's also symmetry. Symmetric with respect, do you know?
Origin.
That's right, the origin. What's that mean? That means if you were to take a nail and put it into the origin and spin it 180 degrees around the nail, you'd still have that function back. And so actually, here's my pictures, right? There's an even function, there's an odd function. And by the way, notice what they're doing here. They're giving me some rules about if I'm integrating, not from A to B, but from, say, negative b to positive b. So if my a is actually negative whatever the upper limit is, then nice things happen because of symmetry. And so I think Stephanie asked me a question last time, and I think I used this property with you guys, right? I remember I split it into two integrals, and I said, but they have to be the same because the function was even. So that's why this area is the same as that area. So then you can just replace it with a 2. And now think about it. Don't we love when we get a 0 here? When you plug in 0, that's easy, usually. Plugging in whatever the other number is, you might have some calculations to do. But an odd function is even better. Why? Well, yeah, this means... Why did they color this red? It's like negative area, right? But if you're integrating from negative b to positive b, that means this region has the same area as this region because we said symmetry. Spin it, right? It looks exactly the same. So if this area is the same as that area, and this is positive 17 and that's negative 17, then what's the value of the integral? 0, always. Right? And so now it's just a matter of recognizing when does that happen. So there's some examples in the homework that I want to go through kind of as practice exercises with you to try and see when that happens, okay? But that's part 1 of what's involved in section 4. Not a hard concept. They're going to talk about it here. Oh, I have 2 other things to do in section 4. The second one is called the average value of a function. So we're going to talk about how you find an average. That's the other thing I'll do, but I want to do that in a little bit. It'll be after 9 by the time I start that. And then the last thing in this section, well, the mean value theorem for integrals. Only problem, we skipped the mean value theorem, right? So we haven't even done it for a regular function yet. So I almost think it might be smart to wait till Monday when I cover mean value theorem to really talk about this. But at least we can do the first two. All right, let's do the first two. So let's take examples of using symmetry. Symmetry and definite integrals. Yeah, that's a nice. Use symmetry to evaluate these integrals. Draw a figure to represent your result. Here they say they don't need a figure. All right. So let me do a couple of these. So I assigned the mod 4s. Oh, 14. That's a nice one. Maybe I'll do that. Well, I'll do 12 first. Then I'll do 14. Here we go. Everybody write down number 12 and number 14. Those are our problems we're going to try. All right. Number 12. Integral. Did you get the answer yet? Not yet. Keep working. I've got it. Is the sine function even or odd or neither? Well, if I knew the answer to that, I could solve the problem. Here, let me record this. Oh, I am recording it. Awesome. 0! Ha! Why? It's an odd function. No work necessary. Well, maybe because sine of x is odd. Is that true, by the way? Is it true that the sine of negative x is the same as negative sine of x? Is that true? I guess the way to check it, think about your trigonometry class. We always did the sine from the unit circle. Which coordinate was it on the unit circle? The sine is the same as which coordinate? The y coordinate, right? So let's say I take the sine of, I don't know, give me one that you guys know. Negative what? How about pi over 6? What's the sine of negative pi over 6? Nice job. Who's your trig teacher? All my trig students are absent today. Sine of negative pi over 6. Got it, Steph? Almost. It's negative something over 2. Well, it's negative 1/2, but we're happy. We knew it's one of those, right? Negative pi over 3, I guess, would be negative square root. But the point is, the sine of negative pi over 6 is the same as negative sine of pi over 6, right? Because what's the sine of pi over 6 then? 1/2. You see it? Because as this goes down, that goes up, and it's the y coordinate that's changing, right? If this coordinate is x comma y, you could say that this coordinate is x comma minus y. That's the point. So once you know that sine is odd, then my rule says the answer is 0. That's beautiful. Sam?
What about the other trig functions?
What about the other trig functions? That's a great question. So looking at the unit circle, what if you have the cosine of negative x? Wouldn't that be the same as the cosine of x? Right? Because if I rotate down or I rotate up, the x coordinate, which represents cosine, is the same. You guys see that? Or think of the graph of cosine. What's the cosine of 0? So the cosine function goes through 0, 1. And so it looks like this, right? So it's definitely an even function. What about the sine? What's the sine of 0? And so the sine function goes through, right? And then it starts the loops this way. It's odd. What about tangent? Well, let's think about that. Tangent of x is the same as sine of x over what? Okay. So now let's do tangent of negative x. Tangent of negative x. Well, that's the sine of negative x over the cosine of negative x. But the cosine of negative x, that's the same as the cosine of x. Because we just said that. Cosine's even. What about the sine of negative x? What's that the same as? Negative sine of x. And so this is equal to negative tangent of x. And so what does that tell me about tangent of x? Tangent of x is what? Odd. Cosine of x, I said, is even. Sine of x is odd. Sam, is that enough, or you want the other ones? The other ones are the reciprocals. All you're going to do is flip the fractions. So cotangent is also odd. Secant is even. There they are. Okay? Guys with me? So we should be able to do 14 then, right? Because that's a bunch of trig functions. Here, let's throw 14 back on the screen for you. 14 says this thing. See if you can work out what the answer to 14 is. If you can, then I'd say we're ready for this section. I need a blank sheet of paper. I'll write it down. We can get to work. I want to start off just by showing you how I would rewrite number 14 as 3 integrals like I'm talking about. Let me write it down here. Do you see how I did that? If you're taking antiderivatives of a sum, you can kind of split it up into 3 integrals. So let me pause while you get that down, and then we'll go through it. All right, we good? So let's see. We want to integrate. Does this make sense, first of all, what I did? You can split it up? Okay. Now, what do you know about this function? Is this function even, odd, or neither? Yeah, if cosine of x is even, cosine of 2x is even also, because you could throw a negative in there and the 2's not going to change that. Cosine of negative 2x is the same as the cosine of positive 2x. Does that make sense? So if this is even, then what can I do? Well, I claim that for an even function, we can say that this equals twice the integral from 0 to pi over 2, cosine of 2x dx. Does that help? Actually, this trick might have helped on some of the problems from last night's homework. I mean, they assume you already covered this section. So maybe that would have helped. I don't know. Plus. Okay, next. What about this function? We have cosine of x, sine of x. Is that function even or odd? Cosine of x, sine of x. We've never done that. Let's see. If you did f of negative x, you'd have cosine of negative x, right? But cosine of negative x is the same as the cosine of x. And the sine of negative x is the same as negative sine of x. So do you see that this is odd? If that function is odd, then what's the value of this integral? 0. So that's really nice. Bless you, Nick. Okay, finally, minus 3 times. Okay, well, let me write this one down again. I just want to point out that you can bring that 3 past, because it's a constant. We've done that before. Okay, what about this function? The sine of x to the 5th. Do we know anything about that? Well, let's try it. Let's say that g of x is the sine of x to the 5th. And let's think about g of negative x. Well, that's the sine of negative x to the 5th, right? Well, negative x to the 5th, that's the same as the sine of negative x to the 5th, because you have 5 negative signs in there. So you can pull it out of the x. And now what do we know about the sine? Is it even or odd? So that equals, because it's an odd function, negative sine of x to the 5th. And so g of x is odd. Well, if this whole thing is odd, then what's this all equal? 0. So talk about a time saver once you recognize this stuff quickly. You have this huge integral to do in problem 14. You know? You go back and look at it, and you say, at first glance, it looks like it's going to take a long time. But it turns out the only part you really have to integrate is the very first part. Cosine of 2x. And it's twice the value that you would get if you just went from 0 to pi over 2. Actually, I should show you that. Here, let me go back to the calculator. So I'm going to go to the y equals screen, clear out some of this stuff, and I'm just going to graph cosine of 2x. Okay. And I want to graph it. There it is. And so I'm saying to get the answer, all we have to do is integrate, so second calculate, and this is choice 7. And what are the limits I want? Well, I said we'll do 0, and then we can type in pi over 2 here. Here's pi divided by 2, and it'll integrate it for me. Oh, look what it got. 0. So I just need to do 2 of those. And then I get 0. Are you with me? Yep. Jessica?
Why did you choose because
Oh, instead of negative pi over 2? Yeah, that was because I had used the fact that it was even. Now, you're right. You guys understand you don't have to use even and odd properties. We could do this. We could say, okay, we're going to go second calculate. What would I say? Oh, choice 7 again. What if I went from lower limit negative pi over 2 up to pi over 2? Would I still get 0? Should, right? Because now you still have just as much below as you do above. You see that? It doesn't say 0. What's it say? Really small. Negative 2.51 times 10 to the negative 14th. That's a seal number, right? 0.0000000000251. That's pretty close to 0. Oh, why did it do that? Someone asked. Tim? Because remember how the calculator does calculus. It does not do antiderivatives. What's it do? A whole bunch of rectangles, right? Left sum or right sum or something like that. And so it's going to have a little bit of error. And this time it added up. Last time, the amount of error it had was less because you only had half as many rectangles. And so it just registered as 0. But this time there was actually enough error that it thought it was calculating something. It thinks there's a slightly negative answer. It thinks the area below is slightly more than the area above. I don't know. I don't know. That's a good question. I'll be perfectly honest with you. It doesn't do rectangles. I'm fibbing a little bit. We're going to learn in Calc 2 what it really does. So there's an upgrade from rectangles. Okay? Actually, this might make sense to you. Let me draw the picture. The upgrade from rectangles is this. You guys have a curve, right? And so the problem with rectangles is they hang over the edge. So the upgrade is, okay, don't do rectangles. Do trapezoids. Now, is that perfect? No, but it's an upgrade. You guys with me? Then there's one more upgrade from trapezoids. You actually do parabolic curves, and that's called Simpson's rule. And that is what I think it's using. There are upgrades from Simpson's rule too, but they take a long time for your computer to run, and I don't think it does that, because I think it would take too long. But I didn't program it, and it's not like they'll show me the program. But those are good questions. I think it does Simpson's rule. That's pretty standard. So we'll learn about that in Calc 2. You guys have other questions so far? You guys are asking good questions. I only have 10 minutes. I still have to cover the average value of a function. So I'm going to see if I can do that. Let me show you what one of the exercises looks like first, okay? Here, let's go to the exercises. And let's zoom ahead to where they start talking. Here we go. Average value. Find the average value of the following functions on the given integral. Something like number 30. I like this one. It says the elevation of a path is given by this function, where x measures horizontal distances. Draw a graph of the elevation function and find its average value. I did this yesterday. It was nice out. I went for a run in my neighborhood, and there's you go right around Shaker Lakes. But I have this app, Runkeeper. You guys use an app when you work out? Probably some of you do. And what it does with the GPS, it measures your elevation, so you know if you ran up or down a hill. It's kind of nice. So we can do that for this problem. They're telling me, hey, take out your graphing calculator. This is your GPS thing. And in the y equals screen, let's type x cubed. They told me to use technology for this problem. Minus 5x squared plus 30. Oh, it doesn't give me the units. That's too bad. It just says the elevation is this. Well, let's graph it. Let's go to Zoom Standard and see if it graphs it. Oh, it's going to miss. Well, yeah, I don't see it very well. How come? What's the y-intercept of this function?
30.
Yeah, plug in 0, you get 30, right? So we need a better window. Well, they tell me what they want for the x's. They say, look, x is going to be between 0 and 4. So let's go from 0 to 4. Hey, let's pretend those are miles. So I'm walking 4 miles, or I'm running 4 miles. Okay? And then what about y min and y max? It's not miles anymore. But we know that we started at 30. So why don't I go from, say, 0 to 50? Let's see if that works. This okay? And then I'll put a mark every 10 so we can kind of gauge what's going on. All right, let's look at the graph. There it is. Oh, I like this kind of run. Yeah? So I started at 30 what? I don't know. Miles? No. 30,000 feet above sea level. I was at the top of Mount Everest. No, I don't think so. Well, whatever the units are. And then I dropped down. How low did I get? Well, here's 10, right? I never got to 10. And then at the end of the run, I had to climb back up. It's tough. You guys with me? So now the question is, what was the average elevation? Well, I would say it's less than 30, definitely above 10. Was it 20? Was it 15? And what do I even mean by an average? Can you compute that? I mean, I've never in class had to explain to anyone how to compute what their average is in the class. Right? I've taken 3 exams. I add up the 3 exam scores and divide by 3.
Would it have something to do with how long you actually spent there, having something to do with like the derivatives and stuff?
It does. And even more so, the antiderivatives. We're going to see this. And see, I think this is actually really cool. So let me go back to what the book says about this, because I thought they did a nice job of explaining it. Here, average elevation, they're doing a problem also, a hiking trail. Fine. But let's look at this process here. They say, hey, look, they're actually explaining what I said I never had to explain. What's the average weight of 5 people? Add them up, divide by 5. Like, yeah, nice. That's really a nice calculus class you're in at Lakeland. All right, so then consider a function that's continuous on AB. Right? That's the difference. It's not like I have 5 test points. I mean, I guess one way I could do this, I could take, if I'm running for 4 minutes, I could look at my elevation at the end of minute 1, minute 2, minute 3, and minute 4, right? All of a sudden, it's starting to sound a lot like a Riemann. What's the word? That's a sum, right? A Riemann sum. Because you're finding the height at each particular point. So that's what they're saying here. And then divide by n. Okay? Now, let me write this out. I mean, here's my elevation, right? Actually, this is almost it. It went back up again. And so if I wanted to know the average height, the average value of a function, what do I do? Well, I can compute the value at n points, add them all up, and divide by n. That's the idea. But that won't be perfect. There'll be error. So how do you reduce the error? What? More points. But how do you remove the error? You need to take the limit as what happens? As what? Right, as we called it delta approaching 0. That'll make n go to infinity, right? And so the game was, we're going to add up a bunch of xi stars, but then divide by n. That's what I want, right? This is the average value. Well, that's almost what I have. There's only one more thing I need to make this an integral problem. This is almost 1 over n times the integral of f of x dx. There's only one piece missing. What's the only piece that's missing? Right here. Do you remember what we used to have right there to make it the Riemann sum? Delta x, right? What does delta x usually equal? Do you remember when we split it up regularly what delta x equals? There you go. I have the n. You see it? So to get it to be this, what I do is I put the n in there, and I also want to put a b minus a in here to get that. And so what I do is I say that the average value, and this is your definition, the average value of f of x on the closed interval a, b will equal 1 over b minus a, because I had to get that involved, times the integral from a to b f of x dx. That's the average value of the function. Okay? So let's try it for our problem. What number are we doing? We're doing, oh, I lost it. Where was that problem? That's a good problem. 30? 30. Draw the graph of the function. Find the average value. Okay. So the average value for 30, well, let's see. I need to integrate. First of all, I have to do 1 over b minus a. So that's 1 over 4 minus 0. Because 0 and 4 are the endpoints of my integral, right? 0 and 4, let me get that calculator back up there, are the endpoints on my picture, right? So I do 1 over 4 minus 0, integral 0 to 4, and I have to write down this x cubed minus 5x squared plus 30. So here I go. Let me throw that back up for you. Right? And so I get, let me integrate this, 1/4 is what 1 over 4 minus 0 is. And then I get 1/4 of x to the 4th minus 5/3 of x cubed, because that's what's going to happen to those constants. And then plus 30x. I don't need to put plus c. I just need to put a 0 and a 4 here. So let's see what I get now. Plug in the 4. 1/4 times 1/4 of 4 to the 4th. A lot of 4s. Minus 5/3 of 4 cubed. Plus 30 times 4. Huh. How about that? And then you'd subtract 0, right? Because when you plug in 0, all right, guys, I'm at the point where I just don't want to do it that way. I want to use the calculator. But you get the idea, right? So the answer is, here, let me go second quit. All right, here I go. They say use technology. And we have to go anyways, huh? Is that what I'm hearing? Yeah, it's 9:25. But the last thing to show you, this is worth showing before we leave. They show you up here this little graph of the average value. Where'd it go? Here. The average value let's say this is my average elevation. See the area of this rectangle? What's the area of this rectangle? It's the average value times b minus a. Well, if you multiply the average value times b minus a, you just get the value of the integral. So it's kind of like you can see that this green has to match the error over here. And I think that's really kind of cool. See that? All right, we'll talk more next time. You guys have a great weekend.